Now let's start. Consider four poles on the opposite sides of the road, and let's draw two triangles by joining the height of the poles. So by looking both the triangles, can you tell me what is common in both the triangles? They have a common base, and also they have the common height, because if we see the boundary of the road, these form parallel lines, and we know that the distance between two parallel lines is always constant. Therefore height and base both are same for these triangles. Okay, so when we calculate the area of triangles, we use the formula 1 upon 2 into base into height. Since height and base in both the triangles are equal, so its area will also be equal. This implies a property, which is triangle drawn between two parallel lines with the same base have equal areas. Let's try in a different example. So we are going to take another example for this concept. Okay. Now consider a single light pole on one side and three light poles on another side of the road. Okay, and again we draw two triangles by joining this line. Now can you tell me what is common in this triangle in terms of base and height in both triangles? Yes, height will be common, but the base is not common. Base of both the triangles are different. Now by the triangle we can see easily that we draw a line in a single triangle to split out in two different triangles. Here we don't need even the parallel lines to show the height is common in both triangles. So the conclusion is, if we draw two triangles by splitting a triangle, then height of all the three triangles will be equal. Okay, but ratio of their areas are equal to the ratio of their bases, because when we take the ratio of the areas, the constant terms are cancelled out. Here you can see 1 by 2 is cancelled by 1 by 2, and height is common in both the triangles, so height will also be cancelled. So about both these two properties, and these two properties, we are going to use these two properties in a important theorem, which is BPT. So let's start. We are going to prove that if we draw a parallel line in a triangle to the base of the triangle, then we see that other two sides are divided in same ratios. As you can see, here we draw DE parallel to BC. Then we observe that AD upon DB is equal to AE upon EC. And given what is given in the question here, you and I can fairly see D is parallel to BC. And what we have to prove? AD upon DB equals to AE upon EC. So now consider in triangle ABC and triangle ADE. What you can see, we have to take out AD upon DB. So we construct a line BE. We join BE. Okay. So you can see area of triangle ADE equals to half into base into height. And what is the base? AD is the base in triangle ADE, and in triangle BDE, half into BD into height. Now we will find ratio of their areas, because we can see we want to find the ratio of AD and BD. As you can see here, when we are find the area, the ratio of the areas of two triangles, here the constant terms are cancelled out. Then what we have? AD upon BD. So it is our first step, and it is very simple step, and similarly we will do the second step same as we did in the first step. There again two sides. We see in the right part what we have to prove. We have to prove AE upon EC. So consider these two sides in both triangles and try to look where these sides are. So by similarly as we did in the last step, we construct we construct DC, a line, and following the same steps as we did recently, area of triangle ADE upon area of triangle CDE equals to half into base into height. And what is the height? Height is AE, and in the triangle CDE, height is EC. Sorry, these are the base. Sorry. These are the bases. Height is same, so we will cancel out height by height and 1 by 2 by 1 by 2. Then we will have AE upon EC. We can say area of triangle ADE upon area of triangle CDE equals to AE upon EC. Now we have equation first and equation second. As you can see, we have both AD upon DB equals to AE upon EC in equation first and equation second. Now let's begin the third step, which is the last step and important step.